Yeah. And oh, wow. Wow. Because that's why you're the poet, because poets have these issues. Seriously. Yeah. It's true. Yeah. I thought you fixed the problem. Ah, it's always fixed my problems. So, okay. Actually, yeah. Ooh, Sophia. All right. Okay. Okay, 3 minutes. Okay. All right, folks, class starts now. So, uh, well, I'm not going to go and go over that material again. I'm going to go over that material on Sunday with Thomas Garrett, my student, and then I'll upload. That's the stuff that was confusing. And maybe I'll go over that stuff on Wednesday again. So and then there's no class on Monday because I have to go to court.
Right now, no, wait, right now.
Oh.
That's the whole reason you gave us.
No.
No. Speak your truth.
But I'm going to the court because where's the third? Yeah, no, actually, they delayed the prosecution of that dude. So rather than, the dude who tried to, the Mr. T, so now they're after me. Maybe is that better? No, slightly. It's not so funny, but no. No. Okay. Anyways, no quiz today. It's going to be next week. Yeah. All right. So I know. The quiz is open book, discussion free, and I walk around. So, all right, folks. So, everybody's heard of the vertical line test. Randomly, I thought I will start here. What does it mean to have a vertical line test? Here's the graph. What is this? Function. Very nice. So, this is a f of x function here. And then this is where our x's go. And this is where the y or y equals f of x. You've seen all this in elementary school. Vertical line test says take a marker and draw vertical lines. Okay, so I put 4 lines, and if there's an x here, how many points does this vertical line touch on the graph? 1. Only one, only one, only one. So if we thought of this region as our set A, and then this region, let's say, as our set B. So I'm bringing that stuff again. And so then these would be, and maybe this goes like that. Okay. So A, B, what kind of picture are we getting here? Let's say 4 points. And there are many other points that are, so this would be what? Very good, because there are things that are not getting arrows. Not everything gets an arrow. Not every point gets hit, supposedly. Something like that. All right, so this is injective. Okay, let's go here. We draw just one vertical line, and the problem now is, so we have 1 point here, and this goes to 2 different values of, let's say if this was A here. So why is this wrong? In other words, if this is, let's say -3, and the function was x squared, Yeah, it should always give you one. In other words, this is fine, right? This picture is fine, is it? If this is -3 and this is +3, if you put in -3 into x squared, you're going to get 9, only one value. You put +3 into x squared, you get 9. You put -3 into the same function, and you get this just one output. So in other words, if it is like a wedge, like an arrowhead, this is a function, this is legit, legit. This is wrong. When it's pointing to the left, if the arrow is pointing to the left, then this is not a function, not a function. And that's what the vertical line test says, that for one input, if you get two outputs, actually in this case 3, then we are not dealing with a function, but perhaps a relation. Okay, so yes. Yeah, we're pretending that. Let's say it's going to be something else. This is actually x cubed kind of thing, not x cubed. What is that function that becomes an s? I think it's it is x cubed. X squared looks like this.
Oh, yeah, sorry, it is x cubed.
Yeah, so this might, an x cube is actually maybe, is this x cube? Maybe this is x cube. This might be. So this is x cube. No, this is something else. This s thing. Oh yeah, it's not one of the functions. That's right. It's just a relation. Okay, all right. Let's do one more, and then we're gonna move on. And let's draw. So that what I was trying to do today was to kind of think about a vertical line test with our little eggs and arrows. Yes, RGB. Also, this could be, this could be x cubed. Yeah, it looks closer to that, but all you have to do is Google it and you can find all the graphs for these. And I don't seem to have them in my head right now, but yeah, so it's actually like this. Is that what x cube is? Yeah. Yeah, that was just beautiful swings. And here again, if you do, it only hits 1 point, vertical line test. And so x cube is a function. Okay, now let's do one more. And then we're going to move on to some other more difficult stuff. So this is the easy bit. Okay, we have a function. And I'm going to draw it in red. Let's just draw it in blue. This is 0, 1, 2, 3. And so this line is 4. Okay, so we got a straight horizontal line. And I'm going to apply the vertical line test. And of course, this is our function f of x. Is f of x a constant function? It doesn't matter what value of x you put in, it's always going to be 4. So if we do our Aggies, so this would be our f of x, right, folks? And then here I can put every point here. This is our A, this is our B. And if I do 2 points from here, what does this look like? An arrow going towards the right, which means this line, horizontal line, is what? A function or not a function? A function. And therefore, we can have more lines going into this. Okay, if this guy went to another place, then then this thing is not a function, but that doesn't happen. Are we cool with this? Let's move on. I was just trying to, this is why I've drawn a circle here. Is circle a function or a relation function? Because, sorry, relation, because vertical line test hits 2 points on the graph. Okay, we gotta move on because this class is not really about that. Okay, so start to go towards something slightly more complicated. Okay. And just want to make sure. Yes, good. Just want to make sure it's getting recorded. Now let's do, we have a, what's my picture here? Okay. All right, we have a function here, f of x. Got x's here and y's here. Okay, so how do we think about this? All right, a. If I put a into this function f, is this function f as it's drawn defined at a or not? Very good. Okay. And then this thing goes. All right. What about now? We have a, yes, we have a function that has the graph like this and an isolated point from this function of this graph sitting right there. Is now a, if I stick the value of a, is the function defined at a? Yes, very good. All right, now I have my friends known as our x's, and they are moving towards, here's our x's, slowly are moving towards, x values are moving towards a. As I put each x value that is closer to the value of a, where is the function moving towards? Let's call this 4, and then this will be our little 5. When I put different x values from the right and left into a function formula, which I don't know what this thing is, the value of the function is moving towards what? Let's call this, we could just make this 6. So I'm putting values like 1, 2, 4. As I get closer and closer, and from this side, maybe I'm doing 10, 9. As I get closer and closer to the value of 6, the function, which is not defined at a, is moving towards what value? 5 or 4? It's a trick question. Yes, very good. No, sorry. 4. Isn't that what's happening? As long as you haven't reached this point, you're going there. So as our values move, so this is the intuitive way of looking at it, and then we're going to do the non-intuitive mathematical way of thinking about this. So we're just doing the standard stuff you've already done in high school or in college. Okay, all right. So we have values of x's that move towards this a, which we are saying is 6. Then the function values goes over there. All right. So does this, so in other words, in the limit, as x, values of x go to a, the value of the function goes to, let's call this L. Vincent, as the values in the domain of the function f, values of x, these are go towards a, which is our 6, then the value of the function tends to L. Is this function defined at a right now? Yes, unfortunately, it is 5. So if I take this out, now, is the value defined at a? No, not defined at a. Does this function still have a limit? Yes, because it still tends to 4 to L. Okay, now what if I did this? Oh, we're thinking about, we're looking at this and going, what is this saying? What does this say if the function is defined there or not? So we're thinking about, no, okay, I know what you're asking me. The topic is that you want to write on your book as we're looking at functional limits, sorry. That is the topic for today. Now, of course, yeah, without headings, you're like, what is this? Yeah, it's about nothing and conversational values. Okay, all right, let's do this. Now, so now this is what? This is a definition of a limit of a function from both left and right. Now, does this function have as x value, so limit of function of this function as x goes to a, where do we put the plus sign? I'm forgetting. Is that right? No, from the, that's right, that's where the plus goes? Okay, thank you. Haven't looked at this in like 4 months. So, does this function have a right hand limit? And what is its value? Anybody? So is that right? Oh yeah, that's right hand is this one. Sorry, good. Yes, who said 4? Very good. So yes, as we move from the right towards a 6 or towards a limit a, the function's value go to the limit. So yes, it does have a limit. It does have a right hand limit. What about left hand? And I might be messing up with the terminology here. Is it left limit or left hand limit? I think it's left limit, right? I don't remember either. I should have looked this up, but let's keep going here. So in other words, limit of x as all the values of x move to a from the left, from the minus infinity side. The value of the function tends to, so I'm going to write here 4. Does it have a left hand limit or left limit or whatever the term is? And what is it? Ryan says 5, and I'm going to go with that because as the values of x go towards a, the function tends to 5. Is this function defined at a? Yes. And in fact, for this one, from the left hand, when we think about the left hand, the function seems to be defined for the point we're interested in, a, and for the left hand one, it isn't, and it doesn't matter. And then overall, does it have a limit? And the answer is no. And what is the formula for that? The limit, the left hand limit of the function better equal the right hand, and then we can say that the function has a limit. overall. Okay, all right. So let's move on. Again, now we're gonna run into, we did that already. Okay, okay, now we're gonna write some sentences and words and, or actually I'll start with the picture. So in fact, we're gonna do a picture first, so. Remember your friends Epsilon and Delta? We're moving towards those friendly creatures from outer space. Okay, so, so I'm going to go straight to the picture and then come back to the definition and all of that stuff. So we have this picture. And here is our function. Now this is not to draw this a little. Here we go. Okay, that is really nice. It's beautiful. We've got X here. And we have, what does the book do? What's Y here? So this is not from one of the textbooks, this is from another. And I have a strip here. So what do I have here? I have a horizontal strip. This line and this line. Yeah, folks? Yeah, okay, all right. And we're gonna say that the limit is right here. And so what should I put here? L minus, write this so that the computer can see this. L minus epsilon and L plus epsilon. So this total distance here is 2 epsilon. And we've been doing sequences and limits of sequence in which we use epsilon on this one here, but we're not, over here we're gonna do, okay, so this is the situation, all right? And so the question that we're asking is, so where is the limit point? It is right here, right? Okay. Can we find, and where is, when we are calculating limits, we calculate limit at a point, and let's call it A. This is the key thing. So the question that is being asked is, does this function have a limit at point A? Looks like it, right? How do you prove that? Well, you have to find a delta that works. Okay, so how big should my delta be? So in other words, we need to find all the points that are moving towards. So in other words, we have that situation where we if the horizontal strip is this wide, then the delta that we need, we'll just use this one here, A minus delta and A plus delta. If this, is this width good? If all the values of X that are close to, that are tending towards A or are actually close to A, do they fall within this strip here? So I am going to do, maybe it's this one here. Oh, sorry. This, oh, sorry. Okay, let me back up. The size of the delta should be, should not matter. It could be very small, right? So for this size of the epsilon, to prove that this function has a limit L, in other words, all the values between these two horizontal red lines are tending towards L. And this is the point of interest, limit at a point. So then, how about this guy here? I'm going to make my epsilon, my delta smaller. This is a minus, and I'm going to make my delta right here. This is our delta, and then what you want is in the cross section, you get this box here, right? Yeah, hopefully I can, and we're gonna make this so it's not defined because that's not important. Because the box, we have found a delta that works for this. Shit, this is not working out, is it? Okay, how do we make this more complicated? Uh, so does this function have a limit? Yes, this function has a limit because given an open interval around the f values around L, this is where the f of x values fall. I can find a delta and x values that in this cross the limit is still in there. Oh shit. Okay. I'm going to make this small. This is not working out, is it? Class is going nowhere. Okay. All right. I'm gonna make this smaller. And I think that the picture has to be works. Okay. Now I'm going to make my horizontal. Maybe I should have just started with the definition here. Okay. How about this? Oh, I'm so confused. Where am I confused about this? I thought I knew what I was going to talk about today. Apparently, there's a when does this not work? Wasn't that? Oh yeah. Okay. Let's do. We need to do when it doesn't work. Through this, I'll have to come back to these pictures and also delete it. But does this have? I'll have to go find the right picture. So what happens is that as you make the horizontal strip smaller, you have to make the delta smaller and still. I seem to have forgotten how it works. No. Okay. Oh. Yeah, this is not what I seem to have lost my completely for all of this. Okay, so before we go home, let's write this definition and then I'll let you guys go. Maybe. Aren't we already halfway through the class time? Yeah, so we have no time left. All right, let's do this. So I'm going to go straight to the definition. If I can find it. Hope I have it right here. All right. Of a definition is very good. Thank you. The limit, the definition limit of a function f at a. Holy Mac. All right, so let's do this. So the reason why I was trying to do that was I was trying to get different directions. Let f be a function. Find at each point in some open interval. I think we'll just focus on the language of this definition today, since my brain is not. Containing A. Okay, how do we show it? And actually, then it says except possibly at A itself. Listen, let F be a function defined at each point in some open interval containing A, except possibly at A itself. So this is a function that's defined for all the points in the open interval except at A. A might not be defined, it could be defined, it doesn't matter. So let's put a graph here. And maybe the speed one, yeah, the speed one. All right, so what is it saying? We have a function f, which is defined at each point. Is it defined for this interval? Yes, we go with that. Finally, I can. No, so this the open interval. Every point in this, so it is defined for A. That works, and that wasn't even necessarily, but for all the points to the right of the A, function is defined, but not. What does it mean to be defined? If you have an X that better hit the curve, and there's a function value right. That's all it means. For every X, you put it into the function X, you will get in return a value of the function. So this is not what the picture is telling us. Let's try again. I mean, the definition wants us to put the. All right. So where should we put it? What about this one? Here's our A. Does this work? And it's not necessarily true that the function is defined at A. For every X, you drew a line, it's going to hit the graph, and the horizontal line will tell you what the value are. Next, is that good? Let's continue then. So now we have an open interval, and what's going to go here? A plus delta. Twist it around. There was a way for me to show that which I haven't done. There, and then this would be A minus delta. We put deltas here and epsilons here. When we are doing sequences, we only use epsilon. Because we are on a number line and there are no two dimensions. We only use epsilon because the values, right? Where are the values of the function? Actually, let's do this. When we put, how did we get this? 1, 2, the subscript. The index numbers was the domain, natural numbers. You stick the natural number into the formula for a sequence, and it spits out the real number. This whole thing is a real number. So this is the output. Just like over here, output is over here. Because of the function's output, we use epsilon up there. Since we put sequence on the real number line, this is where the output goes, which we also use epsilon. This is not where the output is. Then epsilon goes here because that's what we do. Remember, then we have what was it? A plus, A minus, that is the connection. This is where the output goes. The real number line is where the output goes. And if you're talking about a limit, like this one right here, then we say that a sequence has a limit if after a certain term, subscript uppercase L, we start clustering around. something like that is going on over here. So, okay, now it goes. Then, if this is the picture we have, then a number L is the limit of f at a, so I'm going to underline that, if for every number epsilon is greater than 0. So in other words, we don't actually start here. Where do we start? Thinking about a function. We assume the function has a limit first, and then if we assume that the function has a, so we assume the conclusion first, and then we have to show that this is, it's kind of like a reverse thing. So that's why I was trying to do that. There we go. Then let's see. So I'm going to keep writing here, and then I'm going to come back. If for every okay, so if for every number, positive number epsilon greater than that is greater than 0, there is number delta. Okay, so we only have, if we only have this stuff, what does it say? When can a function like this have a limit L? If we have a epsilon, then we should be able to find a delta. So if we have an epsilon, this lecture is not going anywhere. Okay. This is good. I'm not sure though. Anyway, if we have an epsilon, if we have an open interval in which f functional values are fall, then there should be a delta that defines the x values around a that result in f all following here. We actually go from here to here, not from here to here. And I'll actually prep a little harder for this class on Wednesday. No, that's when I'll be in Aurora. Okay, so let's keep going here. And I'm going to write the definition. Right here. Okay. It's such that if then oh, what falls here? What's going on here, folks? Have this situation. We have this situation then, but in fact, what happens is this is what's given to us, what we have, and then we determine the delta. And then once we figure out the delta, then we assume this to be true and that. If all the okay, so let's just try this. That's a delta, right delta. Looks like an F. Okay, still having trouble here, but what? Okay, so even if you're not understanding, what happens is when you do, this is called the epsilon delta definition. thought I could teach quite well, but apparently not. But so how does it work out? You're given this. Yeah, I think I did this better last. What's the other way to say this? This definition, this if-then statement, is same as this notation. Remember, like in sequences, what did we do? We said, that's how I did it last semester. N goes to infinity, goes L, for that. This was equal to same as when n is greater than uppercase n, an, all an minus L are less than n. What does this, if this condition is true, the sequence has a limit. The function has a limit if this is true and this is true. And this condition is on the y-axis and this condition is on the but anyways, so now once more, when you're given this and they tell you prove this, that this function has a limit using epsilon delta definition of a limit of a function. First thing you have to do is what is given is not delta. What is given is epsilon. Now, how do we do a direct proof? We assume this to be true and start here and somehow make our way up here. Problem is we don't have the value of the delta. What we are given is the value of epsilon, value of the limit. What we do is we use epsilon's value, calculate delta. Once we have a delta value, then we can go back, assume this to be true, and start from our assumption from the antecedent and get to the. Okay, so what am I saying here? For today, since things have not worked out, is that we will be given this thing and told, is this true or not? The givens are we never get deltas. We never start here in the domain. We always start here in the. Okay. So, and since we have epsilon, what we really need is delta. So we do scratch work. We figure out what the delta is using the epsilon value, and then once we have that, we assume this true and get it. That's how the proof works. Question or no? Okay, I think stretching. I'm going to not force this. I'm having trouble. I had such an easy time teaching this last time. Okay. It's okay. I can live in shame, dishonor for today. And what are you guys doing? Bye-bye, everybody. Are we done? Good. I don't want to suffer anymore.